All right, ladies and gentlemen, we are now going to talk about our idea of conservation of energy, but we are going to add friction in with that. And with friction is thermal energy, so those two are kind of the same thing. So right now what we have is our law of conservation of energy, and from this law we know that the total energy before any event has to equal the total energy after an event. And we developed this big, long equation. And now that you've done a few problems, you know that you never have all of those at the same time. And even on the U of M test, you would not have all of those at the exact same time. However, you could have a couple of them at the same time. But what we want to look at now are what happens with this law of conservation of energy when we know that in the real world, energy is actually lost. So out in the real world, that when you have an object moving or whatever, energy is lost in many ways. The main loss is usually due to friction, okay? And friction and thermal energy are essentially the same thing because friction causes heat. So oftentimes those two are equated. But you could also lose energy as sound, and you can use energy as light. And if we were to go on with another semester of physics, that's actually where we go into, is we go into the energies of sound and light. Sound and light are both difficult to measure, so we kind of ignore those, and we tend to focus on what we can measure, which is friction. Now, if you were to think about this, if you have a car crash, friction is going to be the most likely source of energy loss. But there's also the nasty sound of the crash, and that is a type of energy that's going to be lost. There's heat energy that's going to be lost. So in a crash, all the kinetic energy that the cars have before the collision actually has to go somewhere. And it usually goes into sound and friction. These are referred to as non-conservative forces. So basically, a cause of a loss of mechanical energy, and I showed you last week, mechanical energy is usually our GPE, our KE, and our PE elastic. Those are our forms of mechanical energy. Usually occur as friction between the object and the surface. It could be air resistance as well. If you're talking about a spring, which is, the equation is 1/2 kx squared, there's going to be friction in that spring as well. So there are all kinds of ways that we can lose heat. So we're going to talk about this loss of heat as mainly work done by friction. And since this work is done by friction, friction times the distance is the amount of work that's done. So this work that's done by our non-conservative forces is usually just friction times distance. And if you want to go that far, friction is the coefficient times the normal force. So the work that's usually lost is the coefficient times the normal force times distance. But I'm pretty much going to leave it as this equation. So what happens now is in our total energy equation, we have the total energy before must equal the total energy after. What we have now is the work that's lost by these non-conservative forces added to the final side. So all of this now is our final amount of energy, and we have this extra work that's added. And again, that work is Fx, or that work is mu times Fn times x, however you want to look at it. Notice that is not on the product or the initial side, okay? So in our problems, essentially what has to happen is we need to account for the energy that's going to be lost and then understand how it's going to affect the object. Because essentially, if you lose energy, that's going to slow objects down. So first of all, what we're going to do is a problem where we don't lose any energy at all. So this is an old problem that we have been doing. We have a roller coaster, Okay, and that roller coaster is sitting at the top of a hill. That hill is 40 meters high. Okay, and the roller coaster is going to travel 7 meters down the frictionless hill. So if we see the words frictionless, that means there's no loss of energy. Okay, and we want to know how fast it would be traveling at the bottom of the hill. So we want to know what is the velocity at the bottom. So this is our traditional conservation of energy problem. At the beginning, all of our energy is gravitational potential energy. Yes, it's moving, but that movement is so slow that we say its kinetic energy initial is 0. And at the bottom of the hill, all of that gravitational potential energy is changed into kinetic. And because of how we measure our height here is 0. So our gravitational potential energy at the bottom of the hill is 0. And then there's no springs involved in this whatsoever, so we have no elastic potential energy. So our equation is a pretty simple GPE initial equals KE final. Oops. So mgh initial equals 1/2 mb final squared. And so this is our traditional problem that you are used to and you've done. We know that mass will cancel here. I want to find final velocity. So v final equals the square root of 2gh initial. And I skipped a lot of math in there, so hopefully you can get to that point pretty quickly. And then solving for the final velocity, just so I have a reference, gives us 28 meters per second squared, or 28 meters per second. So that's how fast we would be traveling down this frictionless hill without friction. Now what we're going to do is pretty much the same problem, but we're going to say that we have a force of friction that is acting as we go down the hill for a distance of 70 meters. So we have the same roller coaster. We still have gravitational potential energy at the top. We're still going to have kinetic energy at the bottom, but the other issue that we're going to have at the bottom is there is also going to be work done by friction as far as the total energy. Now, this 70 meters comes into play right here. That's the distance that the friction is going to act on the roller coaster. So it's essentially the roller coaster coming down the hill and that particular distance. So now my conservation of energy equation becomes GPE initial, that's all I have initially, must equal KE final plus the amount of work that's done by friction. And I really like just throwing the initial equation as work done by friction as that WF first. So now, if we're going to find the velocity, because that's ultimately what we're still asked, is what speed does this roller coaster have? That means I'm going to need to solve this equation for kinetic energy again, because that's where my velocity is. So I'm going to have to take this work and bring it to the other side of the equation, which means I'm going to have to subtract it. So GPE initial minus the work done by friction is going to equal the final kinetic energy. Now that I have that, now I can put in all my variables. So GPE initial is mgh initial minus the work done by friction, which is Fx, is going to equal 1/2 mv squared. Now, again, what we want to do is we need to solve for velocity because that's what we're looking for. But I'm going to walk you through the math here. I need you to be a little bit careful because I'm going to multiply both sides by 2 to get rid of the 1/2. So when I do that, I have 2 times mgh initial minus Fx and that's equals mv squared. Now, your next thing is to divide by mass, but be careful, when I divide by mass, mass cancels there, but mass does not cancel on this side. Mass is not in both of these formulas, so the mass does not cancel. So that means you're left with v squared equals 2 times mgh initial minus fx all over m. Okay, so be careful with that. I know you guys are used to mass canceling, and it doesn't. And then, of course, what we would do is square root both sides. So that's going to leave me an equation of velocity is equal to the square root of this mass. Okay? And now it's just a matter of filling in all of your variables. Okay? So, in this particular problem, I did have to give you the mass of the roller coaster, which is 500, and that's times 9.8 times the height. What was that height? 40 meters. And that's going to subtract the friction, which was given in the problem, of 1370 times the 70 meters that friction goes. And now just remember that all of that is multiplied by 2, and we're going to divide that by the mass of 500. Okay? So, take a moment, do that math for me. And when you do that, you should get a velocity of 20.4 meters per second. And if you compare that to the original velocity, which was 28 meters per second, you can see that because of friction, we lost speed, which should make sense. Speed should slow, or friction should slow your speed down. And that's what happens in the real world, so we can account for that. Now, a lot of these problems are then going to ask you, what is the percent of energy lost due to friction? So we're going to have to calculate a few things in order to get the percent of energy lost. Energy loss is just like you calculate any percent. It's how much you have divided by the total amount of energy that you started with. So again, we're going to need to do a few calculations here because I have GPE initial, which I have never separately calculated, but that GP initial would be the total amount of energy that I started with. So that GP initial, I actually have to now calculate separately. And if I do that, that comes out to be, what? 196,000 joules. Okay? And then down at the bottom, I had a kinetic energy final, which is 1/2 mv squared. And that's going to be 1/2 the mass, which is still 500. And then the velocity is that 20.4 meters per second, not the 28. 28 would be if there is not friction, but I'm going to use that 20.4. And so that kinetic energy comes out to be 104,040 joules. Okay, so then my percent of energy that's going to be lost is just how much energy did I start with, and then how much energy did I end with, and we'll just divide those two. So I ended with 104.40 joules, and I started with 196,000 joules. Joules, by the way, cancel. By the way, we would multiply this by 100 because it is a percent when we're all said and done. And that value comes out to be 53%. So essentially in this ride, we lost 53% of the energy just on the first hill. And if you're designing a roller coaster, you need to figure out how much energy you're going to lose on each hill. And there's the other fun thing with roller coasters is you will notice that if you have a roller coaster, the first thing you do is you get pulled up the roller coaster by the chain to the tallest hill. And then when you go down, you might go through a loop and you might go through another hill, but you'll notice none of these are ever as tall as the first hill. This is where your total energy starts, and then by the end of the ride, way down here, they try to dissipate as much of that energy as they can. And usually they can't. They have to put brakes on them to slow them down. Okay, so now this particular problem is going to ask you something slightly different. So now I am given a speed at the bottom of the hill. I'm actually given a height of the hill. And what we want to know is what will be the percent of energy that's lost. So again, I'm sticking with gravitational potential energy. I probably should have thrown a spring problem in here. But this skier up here has gravitational potential energy initial. When that skier slides down to the bottom, they get down there, they're going to have some KE final. And this time I know what their final velocity is. It's 22 meters per second. And as far as the GPE goes, I know that the height of this hill was 75 meters, and that's really all I need to know along with the mass. So my equation is going to be GPE initial equals KE final plus the work done by friction. So that's essentially the only new thing is you're always adding the work that's done by friction in this case. And so if I want to find out what the percent of energy is lost, I now actually need to solve for that. To solve for the work that's done by friction, I need to bring kinetic energy to the other side. So GPE initial minus KE final is going to equal my amount of work done by friction. And throwing the variables in, NGH initial minus 1/2 mv final squared is going to equal the work done by friction. Okay, again, mass will not cancel. You're going to have to throw the mass into the problem. So, the mass of the skier is 50, 9.8. The height of the hill is 75 meters. Subtract 1/2 the 50 times the 22 meters. Don't forget the square. That's going to equal my work done by friction. So I'm going to assume you could do the math here, and you should check. So your work done by friction comes out to be 24,650 joules. And that is lost energy. Okay? So that calculation right there gives you the amount of energy that we lost going down the hill. Now, what I want to know is what is the percent of that? So to find that percent, I'm going to take that 24,650 joules, and I need to divide that by the total energy that I started with. And that total energy that I started with was the MGH initial that I had. So, and I never separately calculated it, but it's that calculation right there. So my percent is going to be 24,650 divided by my total amount of energy, which I calculated to be 36,750. Both of those are joules. And we're calculating percent, so we're always going to multiply by 100. And that comes out to be 67% energy is lost. Now, my examples have had a large amount of energy lost. That doesn't mean that there's always going to be a huge amount of energy lost. Okay? So, the last thing that we can look at would be what happens if the problem gives you a percentage. Okay? So now we have this child sliding down the slide. So again, I've stuck with GPE, kind of beating that to death. So the child has GPE initial, but they're going to lose 20% of their energy on the way down because of frictional forces. So what will their speed be at the bottom of the slide? So we know they're going to have some final kinetic energy, but they're going to lose 20% of their energy along the way. How do I account for that in my problem? Well, there's a couple of ways that you can think about this. If we lose 20% of our energy, that means that we're going to have 80% of our energy left when we get to the bottom of the hill. So just thinking about the math-wise here, we know that GPE initial, and we're going to know that we're going to have 80% of that left. So we're going to have 80% left. So we could just multiply that by 0.8, and that would equal my KE final. So you're not really coming up with our work done by non-conservative forces. We're just using that percentage to calculate what we have left. So this would be mgh initial times this 80% would equal 1/2 mv final squared. And if you actually do it this way, and I'm going to tell you that there's more than one way to do this, this mass actually now cancels again. So then this becomes 2gh initial times the 80% is going to equal v final squared. And then taking the square root of both sides, v final is going to equal the square root of 2gh initial. And if you just look at this, that's your initial energy. All you're doing is multiplying that by the percent that you're going to have left and taking the square root of it. Now, this is not the only way you could set this up. It's just the way that works for me. You just got to understand what the final percent is going to be. And if you do this, this comes out to the square root of 2, 9.8. Our height of our slide was 2.5 meters, and times 0.8. And so if you do that, if I did it correctly, that should get us a speed of 6.26 meters per second at the bottom. Okay, so 3 different ways that energy is put into problems. At this point in time, now you're going to try just a few problems where we have to account for the work lost due to friction.